Hello everyone. Today we are going to take a look at something special at Wasm and Wazi, something that is becoming very, very popular these days, and some people even say that it's becoming the new Docker killer. If it's like this or not, let's see. So I will show you what it can do, what it might do, and what it cannot do. But without further ado, let's dive in. So let's start with some basics first. What exactly is Wasm, or WebAssembly as it's called? WebAssembly is something that is running inside a virtual machine. This means that it generates some kind of bytecode that can run on different machines. So it can run on x86 machines, on ARM machines, it can run on macOS, it can run on Windows. So something that is not so different from our actual Java applications. The promise, however, is that it's much more efficient concerning CPU and concerning memory. The question is now, how can I generate this WebAssembly code? And assembly really means assembly, as in the language assembly. There is an option that you can code this directly, but this is as much fun as coding assembly directly. So what you can do is, and what you should do is, you can have another language and then compile to WebAssembly. So the best supported languages are some kind of C types, like Rust or C++ or C. Lesser supported are things like C#, Go, and other things. What you also need, of course, is this virtual machine or runtime. We will see this later. And there is also the promise of Docker supporting WebAssembly directly. So, which basically means that you can run Docker processes along with Wasm module. And this is working, that Docker implements this runtime, which is called Wasm Edge. There is currently experimental support in the current Docker version. And there is the promise that this will be generally available in the future. Okay, let's take a look. So we will start with a Go application. This is a very simple Go application. This has a function that has say my name, and it gets Slim Shady. So if I do go run say my name.go, I just get my name is Slim Shady. Just forget for the other code for now. We will take a look later. So this is a simple Go application, and it's pretty easy. So what can I do to compile this Go application to Wasm? So what I need here is TinyGo. It's not possible to have Go for this, at least not if I want to run this on the server side. I need something that is called TinyGo. There is the option to install TinyGo on your machine. However, I'm using this inside of Docker, and for this we need this very long term. But the opportunity here is that you don't need to install TinyGo yourself. So we can just have this very long Docker run command, which is basically doing TinyGo build and saying please have a target Wazi. We compile this, and now we get a Wasm file. If we take a look at the Wasm file, we don't see much because this is bytecode. So we will see how this looks in text later. Now we have our Wasm file, and now the question is, how can we start this Wasm file? So for this, we need a runtime, and for this, we are using wasmtime. So what I do is say wasmtime, and then say my name dot wasm. And here we go. My name is Slim Shady. The same result as if we say my name dot go. Okay, what's the benefit here? Honestly, not much. So instead of running Go, we are running a Wasm file on the backend. Let's take a look at the next thing we can do. So what we have done here is specifically not Wasm, but called Wazi, which is basically Wasm on the backend. But it all started on the front end with the promise that we can have code compiled very efficient and then run it inside the browser. So let's take a look here. So we have this folder, which is called Wasm, and we have an index.js file here. This index.js file does a lot of mumbo jumbo. I'll leave you a link later in the description where you can look it up. It basically says here in instantiate, say my name from Wasm. So this is also our Wasm file we have compiled earlier on. And now we can actually call our say my name function from JavaScript. For this, we say Wasm module instant export say my name, which is this function. And this somehow executes this function. The problem is, however, that Wasm in connection with JavaScript is not possible to work with strings. So what we need to do is to create a pointer to a byte. So this is what I'm doing here. So I'm not using this function. I'm using this say my name byte, which basically returns a pointer to a byte array. Because this is working with JavaScript, what we also need to do is here say / export say my name for this to get picked up by JavaScript later on. What we get here is only a position on the pointer to the char array, and then we need to do some additional stuff here to extract it and to convert it to a text. But other than that, that's working. So if we have this running inside the browser, I also get my name is Slim Shady. So basically what it's now doing, it's executing the original Go code, or the Go code that does not return a string, but the byte array from JavaScript, which I think is very, very cool. We can take a look in the debugger here. So this is our index.js, which is doing this. Also, what's very nice, we can also now take a look in the say my name Wasm file, because Chrome is able to decompile the bytecode into something readable. And yeah, this is what Wasm looks if it's decompiled into something that looks like a text. And you see, that's very, very complicated. You can code this directly, but I really suggest you not to. Okay, that's my Go function inside the browser. What is worth to mention, if you have simpler functions that only return some things like a int, you can do this easier. So for example, we have a function that is called add. Here, func add returns an int and gets two ints. For this, we don't need to do a lot of conversion like we did here. We can just call the function, we get the result, and that's just working. And this is because with simple types like integer, the Wasm to JavaScript bridge is working. With more complex type, and string is a complex type because basically string is an array of chars, we have to do some additional stuff. Okay, so what's the benefit here again? Of course, calling a simple function that just gives me a name is not so interesting, but Wasm on the front end can do much, much more. There are currently complete 3D engines running in the browser and also games that have the promise of speeding up things inside the browser efficiently. Okay, but as I am a backend guy, I'm now asking myself, there are people who are saying that Wasm is the new Docker killer or Vasi. So what I would really like to do is build a microservice. So let's take a look if we can do this here. So for this, we have a very simple REST service. Building REST services in Go is very, very easy. We just need a main method, a handler function, and then we can just say this endpoint should return hello from Go. So if we say go run REST service.go, starting to serve you. And now, voila, I have a running REST service in Go. Very, very nice. And very few code. So, as we already learned, we can compile our Go to Wasm. As this takes a while, I will not do this now. I already pre-compiled this REST service.wasm file here. And now I will say wasm time REST service.wasm. And what's happening? Honestly, not much. So the application starts and it immediately stops. So I can click here, but there is nothing answering here. And why is that? The wasm time runtime is not ready to do something like HTTP serving. It's only, at least it looks like, you can start an application, you can stop it, but there is no functionality that is doing socket operations like socket accept and something. So this is not working. It compiles the application, it works, but you don't get a working service here. Okay, so I dug in deeper. So what can we do to build services now with Go and Wasm? There is a company that is called Fermion. They have a lot of YouTube videos now on the internet in combination with Docker. And they have a thing which is called Spin, which promises to be a framework for Wasm, for example, also with Go. So what you need to do, you need to introduce this tool, which is called Spin from their website. It's pretty easy, just download and have it somewhere in your path. Then we go to the folder and then we can do some steps here. First step is we say spin new. And now it asks me, okay, you want something that is Wasm or Wasi. Please choose the language so that I can generate a template for you can work with. You see, we have a lot of options here. So let's start with HTTP Go. Now it's asking me, give me a project name. We say test. Ta-da, takes a while. And then we get a new folder, which is called test. Let's go to that folder. Next step would be spin build to build our application. By the way, our application looks like this. Also a simple handle, looks very similar to this one, but really only similar. Yeah, but if we say spin build, we get an error. TinyGo command not found. This is because I haven't installed TinyGo directly on machine, but it's running inside Docker. What I can do, however, is execute this command manually. This is very similar to what we did previously. tinygo.build and a lot of parameters, and then it will go and start building the application. It has built the application, and then next step with spin is just saying spin up. And it looks like that we now have a working service. If we take a look here, this generated also a Wasm file. Let's just stop that for a moment. Again, we will have the same problem if I just say wasm time main.wasm. It will do nothing. It will start and immediately stop. So this is why we need this framework, which is called spin, which does some extra stuff here. We say spin up, and now it's running the Wasm file and it's doing additional stuff here so that it's really running. Looks good, looks promising. So let's click the link here. Bam, error 500. So if we go to the backend, we see we get a lot of exceptions here. Why is that? I don't know exactly. The problem could be that we are using TinyGo version 0.26, and it is said that this is not working correctly. We need to use a lower version. However, the lower version is not running with Docker. And this brings us to the point that was already somewhere on the horizon. If we remember, take a look at this graphics here again. There are a multitude of languages that we can use to compile to WebAssembly. The problem is there is really only good support currently for Rust. So at least it looks like. So Go is supported somehow, and it somehow works with some simple examples, but you see if we get into a more complicated example, does not seem to work. Okay, bummer. What can we do? Okay, so if Rust is better, let's take a look at Rust, because there has to be a new language every year, of course. So another project, Rust. We will start with our simple example again. So we will have our say my name, this time in Rust. Honestly, I'm already not the biggest fan of Rust, because this looks like, and this is somehow true, like very old C or C++ code. So it reminds me of the days 20 years ago. And these are days I don't want to get back, but other people see it otherwise. Rust is becoming more and more popular. So nonetheless, this is our say my name function in Rust. So it does the same. It says say my name, Slim Shady. It has a function here that returns a string. Already very strange looking, at least to me, but it's working. We can run this inside our IntelliJ. IntelliJ has good support for Rust, and then we get my name is Slim Shady. Very nice. Okay, let's compile that to Wasm, shall we? For that, we need to say cargo build target Wasm. And the good thing is here that in contrast to Go, which only has some support for Wasm, and no support for Wasi, so for the backend part, Rust can do it all out of the box. So we say, yeah, but we have to be in the right directory, I think. Say my name would be better. So we say cargo build target Wasm. This compiles in a matter of seconds. And then we get our Wasm file now from Rust. It's somewhere buried here deep down below. So if we say Wasm time target debug, say my name from Wasm. My name is Slim Shady, again, with the Wasm file. So that's working, even if I'm missing to see it here somewhere. So Rust to Wasm is working. So now let's again take a look at a more complex thing like a service. For a REST service in Rust, you have to do something more. You need to have this thing which is called a toml file, and you need to have two dependencies which are called Tokyo and warp. Don't ask me why. This is needed if you want to have a simple REST application, and it already looks very funny to my eyes. However, it works. We can run this, and then we get an endpoint, and we can call the endpoint, and we say, hello, yo. Hey, very nice. It's working, our Rust service. Okay, so I think we are good to go. Now we are going to compile this thing again with our awesome Rust compiler to Wasi. Now, let's again be in the right directory, REST service, cargo build. And unfortunately, we get a lot of exceptions during compile. At least we get this time exceptions during the compile. And because the problem is here that this framework, and this is already a simple framework, is currently not able to be compiled to Wasm. Huge bummer. I don't know. I think it could be possible if you have more knowledge concerning Rust. I think it would be possible to compile this, but then we would still have the problem that if we would start the application with Wasm time, it would pretty much again still start and stop again. So dead end here again. But we remember that we have our fermion spin here. And we can now do the same we did with Go a while ago. So we do again say spin new. This time we pick Rust. We say test. And this again generates a template. This time it generates a template with Rust, which is for some odd reason called lib.rs. Well, looks like some kind of service thingy. We can say spin build, and this, if we are in the right directory again, we can say spin build, and this time this works. It now This looks very, very promising. It compiles, puts in a lot of dependencies. This is much, much faster than with TinyGo. And now we can say spin up. And off we go. It's working. So the same example that failed with TinyGo is working with Rust. If you take a look in our processes here, there are several small things running that are called spin. Yeah, you see it here. They are not using a lot of memory, but as you see, the wrapper that is able now to run our application, our microservice in the background, needs some additional processes here. So if we stop our application that is running with Wasm, the process should stop. It's important to note that in the end, we still have a Wasm file here again, but it's the same situation. If we go to Wasm Vasi, this time release, somewhere down deep, and we say Wasm time test.wasm. Again, nothing happening. Start, stopped. That's it. So we really need the spin framework to do the heavy lifting here for us, for this to work. Let's do it again. Test, spin up. So this is really the first time that we see a Wasm microservice working. So the question is it worth it? And honestly, I don't know. While there is a promise that WebAssembly files are much smaller, which makes the image much smaller and much more efficient, we can also again take a look at our Go project, where I have a much more sophisticated application, service application, which resembles the calling service that I have also for Java, with a health endpoint, and which has some endpoints here. So I can run this with Go, of course, and what I can, of course, also do, I can build a Docker container from this. Very easy, very lightweight. It builds the container very fast. And now I'm running the same application inside the Docker container. And if we take a look at the stats, Docker stats, one thing, we see the thing is consuming 5 megabytes of RAM, and it's also blazingly fast. So if I do load test, this is really, really fast, much faster than Java or Java native applications. And also from an image perspective, so how big is the image size here? Let's take a look. So the image is 17 megabytes. Wasm files can go lower to 2 or 3 megabytes, but 17 is already very, very low. And this is with an Alpine image. There is even the option for Go to have a scratch-based image and build things statically, and then you go down to 4 or 5 megabytes of RAM, which is not much more than WebAssembly application. So at least on the backend side, there is the question, what does it bring to the table of having the extra effort of compiling Go to Wasm or Rust to Wasm instead of having a container directly? And for the moment, honestly, I don't know. On the front-end side, at least there is a promise to speed up things that need to be much more efficient. But on the backend side, I think this is still very early days. We are still waiting for the Docker support to come, and yeah, let's see how things progress here. Okay, that's it for today's video. Thank you so much for joining me, and I hope to see you in the next video. Bye.